Hello, and welcome to Stellar Sleep Tales. This is your place to relax. Let the day slip quietly into the background, and, if sleep comes, drift off while the world continues its gentle rhythm. Tonight, we're exploring something familiar but often unnoticed: the quiet science of rain. Those drops that tap on rooftops, slide down glass, and sink into the ground are part of a delicate chemical process that shapes the air, the land, and even life itself. Before we begin, I'd love to know where you're listening from. Maybe you're wrapped in a blanket, or perhaps you're on the other side of the world, watching rain fall outside your own window. If you enjoy these calming journeys, a like and a subscribe would mean a lot. And to those already part of this small but growing community, thank you for keeping it alive. Don't worry, I'll try not to make this so interesting that you stay awake all night. But if the story of rain keeps you listening a little longer, at least you'll drift off having learned something new. So, let's start. Have you ever wondered why rain isn't just plain meteors falling from the sky, but carries scents, colors, and even hidden ingredients from both the air and the ground? Rain is one of those everyday wonders we rarely stop to think about. It falls in countless drops, nourishes crops, washes streets, and yet behind its simple appearance lies a deep world of science. Talking about rain is really talking about chemistry in action, reactions in the sky, changes in the air, and a cycle that's been running since long before humans looked up at the clouds. At its core, rain is more than water falling from above. Each drop carries invisible passengers, tiny bits of dust or salt that helped it form, gases that change its makeup, and even microscopic traces of life. In many ways, it's a chemical story written in water. Sometimes rain leaves behind that fresh, earthy smell. Other times, it shapes stone, feeds crops, or clears the air. For something so gentle, its impact is huge. In this journey, we'll move from the very small, the bonds that hold water molecules together, to the very large, the global cycles that carry rain across continents and oceans. We'll listen to what storms can teach us, uncover the minerals and gases inside each drop, and see how rain has influenced not just nature, but human history and imagination. As you relax, remember, every rainfall is part of an ongoing conversation between the sky and the earth. It's chemistry written softly in water. Now, let's step into the first chapter, the story of how a single drop of rain begins. Far above us, in skies that may look clear and empty, something is always happening. Water, the same water we see in glasses, rivers, and oceans, is constantly escaping into the air as vapor. This process is called evaporation. You've seen it before: a puddle shrinking on a warm day, or a wet shirt drying on the line. That's evaporation on a small scale. On a global scale, it's massive. Every lake, river, and ocean is sending water into the atmosphere, molecule by molecule, drop by drop. This happens because water molecules are always moving. At the surface of any body of water, some move fast enough to break free from the liquid and rise as gas. Temperature is the key. The warmer the surface, the more molecules have the energy to escape. That's why the sea seems to steam more on hot days, and why tropical regions release huge amounts of moisture into the air. But evaporation also happens in cooler weather, just more slowly. The atmosphere is like a giant storage space for water vapor, but vapor alone doesn't make rain. Water molecules floating alone in the air are invisible and can travel far without ever forming a drop. For rain to form, water needs a starting point, a seed to gather around. This is where nucleation comes in, one of the hidden steps in making rain. The air isn't perfectly clean. It contains dust carried by wind, sea salt from waves, ash from volcanoes, soot from chimneys, and pollen from plants. These tiny particles are called cloud condensation nuclei. When water vapor meets these particles, it clings to them. One molecule joins another, then another, until a tiny droplet begins to form. Without these impurities, rain would be rare. Pure, dust-free air actually resists condensation. In labs, scientists can create supercooled water vapor that won't condense unless something triggers it. In nature, those tiny particles are the trigger. What we might think of as dirt or pollution becomes, in the sky, the framework for clouds. But even when vapor meets dust, a droplet won't always form. The temperature and pressure have to be just right. Higher up, the air is colder, which helps vapor condense. That's why tall clouds form when warm, moist air rises and cools. Lower pressure at high altitudes also helps water molecules stick together instead of breaking apart. The birth of a raindrop is all about balance. Too warm, and the molecules scatter. Too cold, and they freeze into ice crystals. Just right, and liquid drops appear. You can think of each droplet as a tiny worker in the sky, turning invisible vapor into something you can see and feel. Millions of these droplets form at once, creating a cloud. A cloud isn't a fluffy lump of cotton. It's a huge collection of droplets, each smaller than the width of a human hair. They stay in the air because rising currents push upward while gravity pulls downward, keeping them suspended. Inside the cloud, droplets bump into each other, merge, or even evaporate and form again. It's a constant cycle of change. This shift from vapor to liquid is the first big step in the chemistry of rain. It connects oceans to the sky and sets the stage for everything that follows. Even before a single drop reaches the ground, countless physical and chemical interactions have already taken place, molecules escaping heat, finding particles, clustering together, and following the rules of temperature and pressure. When you stand under a cloud, you're standing beneath billions of tiny droplets, each one a small success in the unlikely process of condensation. The sky may look simple, but hidden inside is a complex and beautiful system of chemistry at work. Small enough to escape the naked eye, yet powerful enough to reshape the world below. It's remarkable to think that something as ordinary as a speck of dust, a grain of salt, or a drifting bit of pollen can be the very starting point of rain. Without these tiny particles, the air could hold endless vapor, but the sky would never release a single drop. With them, water finds its anchor and the transformation begins. The chemistry behind this is quiet, almost hidden, yet its results are familiar to every living thing, from the smallest puddle outside your door to the most powerful thunderstorm. It all starts with this silent moment when vapor surrenders its freedom and becomes liquid again. If you asked a child to draw a raindrop, chances are you'd get the classic teardrop shape, pointed at the top, rounded at the bottom. That image has found its way into cartoons, weather icons, company logos, and even road signs. But nature doesn't follow our crayon sketches. In reality, a raindrop's shape is decided by the combined force of physics and chemistry, and the truth is far more interesting than the drawing suggests. When water hangs in the air as a droplet, one of the main forces shaping it is surface tension. Think of water molecules as friends holding hands. Each one clings to its neighbors through hydrogen bonds, a subtle attraction between the slightly positive side of one molecule and the slightly negative side of another. At the surface, where there are fewer neighbors, this pull draws inward, creating a kind of skin that tries to keep the droplet's surface area as small as possible. Left alone, surface tension shapes a droplet into the most efficient form, a sphere. That's why tiny droplets, like mist or the dew on a leaf, are perfectly round. At such small sizes, surface tension easily overpowers other forces like air resistance or gravity. Mist drifting through the air is made of countless miniature spheres, each no wider than a strand of hair, floating gently because their internal cohesion is stronger than Earth's pull. But raindrops don't stay tiny forever. Inside clouds, droplets bump into each other, merge, and grow. Once they reach a certain size, the balance between surface tension and outside forces begins to shift. Gravity starts pulling harder, and as the droplet falls, the air beneath it pushes upward. It's a bit like sticking your hand out of a moving car window. The air presses against it. A falling raindrop feels the same push, but its delicate spherical shape is easier to squash. Medium-sized raindrops, about 2 millimeters across, lose their perfect roundness and start to look more like a hamburger bun, rounded on top, flatter underneath. Grow them larger, and the shapes get stranger. At around 4 millimeters, raindrops flatten even more, and the bottom can develop a small indentation, almost like a tiny parachute. If they grow beyond that, they often break apart midair into smaller drops because gravity's pull becomes stronger than surface tension's grip. This means the neat teardrop shape we see in drawings is a myth. A raindrop is either spherical when small, bun-shaped when medium, or breaking apart when large. The truth is less tidy, but far more fascinating. It's worth pausing to appreciate hydrogen bonds here. They last in only fractions of a second before breaking and reforming, yet together they create enough cohesion to shape entire raindrops. Without them, water would behave very differently. It might not even be liquid at the temperatures we know. In many ways, the structure of a raindrop is simply the structure of water itself, made visible. Mist offers a softer contrast to falling rain. In mist, Droplets are so small that gravity's pull is almost nothing compared to the resistance of the air. They drift lazily, sometimes hanging for hours. Walking through mist isn't like being rained on. It's more like being surrounded by countless tiny spheres, each still held together by surface tension. That's why mist feels different on your skin. Not sharp impacts, but a light, even coating. Cloud droplets are smaller still, often just a few micrometers across. To picture that, you could line up more than 100 of them across the width of a single human hair. They stay suspended thanks to gentle updrafts and turbulence inside the cloud. Their weight is almost meaningless compared to the constant motion of the air. Only when they merge into larger drops does gravity finally win and rain begins to fall. It's almost funny how wrong our common image of a raindrop is. Cartoons give them a stylish point at the top. Weather apps use neat blue teardrops. Even road signs for slippery conditions show the same fictional shape. In reality, a medium raindrop looks more like a squashed burger bun than a graceful tear. Not as pretty, perhaps, but much closer to the truth. Understanding a raindrop's shape isn't just trivia, it affects how light bends and scatters inside it, which is what creates rainbows. It changes how fast the drop falls, how much water reaches the ground, and even how soil absorbs it. A perfect sphere would behave differently from a flattened oval, and those small changes in shape alter how rain interacts with the world. Even the sound of rain is shaped by this architecture. Small, round drops make a lighter patter, while larger, flatter ones hit with a deeper note. The next time you listen to rainfall, you're hearing a mix of shapes and sizes striking at different speeds, all orchestrated by surface tension, hydrogen bonds, and gravity. It's easy to forget that every drop above you is a masterpiece of chemistry and physics, not designed by an artist's hand, but by the laws of nature. Each one is a balance between holding together and breaking apart, between floating invisibly as mist and crashing down in a storm. A raindrop may not look the way we draw it, but in its quiet structure, it carries a story far richer than any cartoon could show. And then there's the smell of rain, one of the most instantly recognizable scents in the world. Step outside after a summer shower, or take a deep breath as the first drops hit dry ground and the air changes in a way that feels almost magical, fresh, earthy, and deeply comforting. Poets have celebrated it, perfumers have tried to bottle it, and scientists have given it a name, Petrichor. Behind that soothing fragrance is a mix of plant oils, natural compounds made by soil microbes, and even chemical reactions triggered by lightning. Each rainfall is, in its own way, a complex perfume crafted by nature. The term petrichor was first coined in the 1960s by two Australian researchers, Isabel Baer and Richard Thomas. They wanted a name for the distinctive scent that rises when rain falls on dry soil. The word blends Greek roots, petra, meaning stone, and ichor, the mythical fluid said to flow in the veins of the gods. A poetic choice for what is, at its heart, a very down-to-earth bit of chemistry. Petrichor begins with plants. During long dry spells, many plants release oils that seep into the soil and cling to rocks. These oils serve practical purposes. Some act as growth regulators for seeds, others as deterrents against competing vegetation. Over time, they accumulate quietly in the dust, waiting for the right trigger. When rain finally arrives, the impact of falling droplets sends these oils into the air in tiny bursts, carrying their aroma upward. The scent is subtle, yet instantly recognizable across cultures. But plant oils are only part of the story. Another key ingredient is a compound called geosmin. Its name literally means earth smell, and that is exactly what it provides. Geosmin is produced by soil-dwelling microbes known as actinobacteria. These ancient, abundant organisms are tireless recyclers of organic matter. As they live and die, they release geosmin into the soil. When rain disturbs the ground, geosmin is lifted into the air, and the human nose, remarkably sensitive to it, can detect it at concentrations as low as a few parts per trillion. That's like noticing a single drop of dye in an Olympic-sized swimming pool. Geosmin gives rain its earthy, musty depth, the same note you smell in freshly turned soil or a garden after watering. Combined with the plant oils of petrichor, it creates a fragrance that is sharp, clean, and grounding. Many describe it as nostalgic, carrying memories of childhood summers, running through fields, or standing on a porch as a storm rolls in. Then there is the sharper, almost metallic note that sometimes precedes a thunderstorm. This comes from ozone, a molecule made of three oxygen atoms. Normally, oxygen exists in pairs, but when lightning splits these molecules apart, some recombine in trios, forming ozone. Though unstable at ground level, storms can pull it down from higher altitudes where it is more abundant. The result is that faint, electric tang in the air before or during a storm, a scent that signals both energy and renewal. Together, petrichor, geosmin, and ozone create rain's unique aroma. Not every shower smells the same because the proportions vary. A light drizzle after a long dry spell will release more petrichor, while a thunderstorm may emphasize ozone. A gentle rain in a forest will smell different from rain striking city streets because the soils, plants, and microbes are different. Why do humans find these smells so calming? Part of the answer lies in biology. Our noses are far more sensitive to geosmin than to many other compounds. Some scientists suggest this sensitivity evolved because detecting the scent of damp soil could help our ancestors locate fresh water. If so, our love of rain's aroma may be an echo of survival instincts. Psychology plays a role too. Rain often brings cooler air, softer light, and the rhythmic sound of droplets. Combined with its fragrance, these cues can trigger memories and associations, moments of shelter, safety, or quiet reflection. The result is a sensory blend that lowers stress and encourages relaxation. Interestingly, not everyone experiences the scent the same way. In perfumery, geosmin can be divisive. Some adore its earthy character, others find it overpowering in concentrated form. Yet, in the natural, diluted blend created by rainfall, it seems to strike the perfect balance. Perhaps its fleeting nature makes it even more precious. Here one moment, gone the next, a reminder of the temporary beauty in ordinary events. When you take that first deep breath after a storm, you're inhaling the combined work of plants, microbes, and lightning, chemistry broadcast into the air, tuned perfectly to human senses. Each whiff is a story of patient oils, industrious bacteria, and the crackling power of storms, stitched together into a fragrance as old as humanity itself. The smell of rain is a reminder that chemistry isn't confined to laboratories or textbooks. It's all around us, quietly shaping experiences we take for granted. Whether it's the whisper of petrichor after a dry season, the grounding wave of geosmin from the soil, or the sharp flash of ozone from a storm, the perfume of rain is one of nature's most elegant signatures, a symphony of molecules that makes the world feel both refreshed and renewed. Rain's hidden chemistry, acidity. When most people think of rain, they imagine pure water falling from the sky, a kind of distilled gift from the clouds. In reality, every raindrop carries a bit of chemistry that shapes its character. One of the most important traits is acidity, measured on the familiar pH scale. While we often think of water as neutral, with a pH of 7, natural rain is slightly acidic, averaging around pH 5.6. The reason lies in the atmosphere's carbon dioxide. As water vapor condenses into droplets, it dissolves small amounts of CO2. Inside the droplet, the gas reacts with water to form carbonic acid, the same weak acid that gives sparkling water its fizz. This gentle effect is enough to nudge rain below neutral on the pH scale. This mild acidity is entirely natural and has existed for as long as Earth has had both an atmosphere and water. Far from harmful, it plays a role in weathering rocks, releasing minerals into soils, and sustaining natural cycles. The balance changes, however, when other gases enter the picture. Industrial activity, especially from power plants and vehicles, releases sulfur dioxide and nitrogen oxides into the air. Once airborne, these gases dissolve into water droplets and react to form stronger acids, such as sulfuric acid and nitric acid. Rain carrying these compounds can have a pH as low as 4 or even 3. This is acid rain, a major environmental concern in the 20th century, though its roots go back further. During the Industrial Revolution of the 18th and 19th centuries, coal was the dominant fuel. Burning coal releases large amounts of sulfur dioxide, and in heavily industrialized cities like London and Manchester,
when sulfur dioxide from burning coal mixed freely with rain, the result was not only acid rain, but also thick, choking smog, a soup of soot and acidic droplets that hung in the air. Historical accounts describe blackened buildings, dying forests, and rivers so acidic they could no longer support fish. Even marble statues suffered. Acid rain reacted with the calcium carbonate in the stone, etching away delicate features and inscriptions. The carved faces of history literally dissolved under polluted skies. In forests, the damage was equally severe. Acid rain leached essential nutrients like calcium and magnesium from the soil, starving trees of what they needed to grow. At the same time, it freed aluminum ions that were toxic to roots. Entire stands of spruce and fir withered under the combined stress of nutrient loss and direct acid damage to their leaves. In lakes, fish populations collapsed as acidity rose beyond what eggs and young fry could survive. By the mid-20th century, scientists began to investigate. Researchers in Scandinavia noticed that lakes were dying even far from industrial centers. The culprit turned out to be airborne pollutants drifting across national borders. This was a turning point. Acid rain was not a local problem, but a regional and even international one. Governments began to respond. By the late 20th century, many nations introduced stricter controls on sulfur dioxide and nitrogen oxide emissions. Power plants installed scrubbers to trap sulfur before it escaped into the air. Cleaner fuels and catalytic converters in cars reduced nitrogen emissions. The results were encouraging. In many regions, rainfall became less acidic, lakes began to recover, and forests showed signs of renewal. The story of acid rain is often told as one of environmental harm, but it is also a rare example of how scientific understanding can lead to effective solutions. When rain turns alkaline. Not all rain leans toward acidity. In certain regions, especially those rich in dust or limestone, rainfall can be slightly alkaline. Winds sweeping across deserts lift fine particles of calcium carbonate and other alkaline minerals into the air. When raindrops form around these dust particles, the minerals dissolve, raising the pH of the water. Instead of being acidic, the rain becomes buffered, more neutral, or even mildly basic. In agricultural areas, this alkaline rain can even contribute valuable minerals to the soil. The chemistry of rainfall is never uniform. It depends on the gases in the atmosphere, the presence of dust and minerals, and the geography below. A storm passing over a coal-fired industrial zone in the 19th century would produce rain chemically different from one sweeping across a modern desert plain. Even within the same storm, rainfall can vary depending on what particles and gases droplets encounter as they form and fall. There's an irony here. Rain, which many instinctively associate with purity, is in fact a chemical mirror of the air it falls through. It reflects the history of each cloud's journey, whether drifting above forests releasing plant vapors, over oceans casting salt into the air, or across cities thick with human industry. The acidity or alkalinity of rain is like a signature of the atmosphere's recent past. For most of human history, people didn't realize rain carried such a chemical imprint. It was simply water from the sky, sometimes nourishing, sometimes destructive, but always taken for granted. It took centuries of observation, and finally the tools of modern chemistry, to understand that every raindrop is a tiny laboratory in motion. Its pH is not fixed, but dynamic, shaped by the interplay of natural gases, industrial emissions, and dust carried on the wind. The quiet lesson of rain's acidity is that something as ordinary as a shower can hold a complex record of both natural processes and human activity. Each drop is more than just water. It is a balance of carbon dioxide, minerals, and sometimes pollutants, all written into its chemistry. Thunderstorms, nature's chemical factories. A thunderstorm is one of nature's most dramatic performances. The sky darkens, clouds tower into anvil shapes, and distant rumbles announce the arrival of lightning and rain. To the senses, it feels like a grand spectacle of light and sound. But hidden inside those bolts of electricity and sheets of falling water is chemistry of surprising importance. Thunderstorms don't just rearrange the weather, they change the air itself, forging new compounds that descend to the earth with the rain. Among the most remarkable of these are nitrates, essential nutrients for life on the ground. A single bolt of lightning can reach temperatures hotter than the surface of the sun, around 30,000 degrees Celsius. At that heat, molecules in the atmosphere are torn apart. Nitrogen, N2, and oxygen, O2, which normally exist as stable pairs, are ripped into individual atoms. For a brief moment, the air is filled with reactive fragments that do not like being alone. Almost instantly, they recombine, but in new ways. Some nitrogen atoms join with oxygen atoms to form nitrogen oxides such as nitric oxide, NO, and nitrogen dioxide, NO2. These dissolve into raindrops, where they react further to form nitrates. Nitrates are special because they are a form of nitrogen that plants can actually use. Although the air around us is 78% nitrogen, it is mostly locked in the unreactive form of N2. Plants cannot simply absorb nitrogen gas, they need it to be fixed into compounds like ammonium or nitrate. Lightning is one of nature's original nitrogen-fixing systems, breaking apart that stubborn N2 bond with sheer electrical force and delivering the results back to the ground in every storm. In this way, a thunderstorm doubles as a fertilizer factory. Long before humans learned to make fertilizer in factories, this process was crucial for early ecosystems. It spread life's essential elements across the landscape. The proteins in our bodies and the chlorophyll in leaves can trace part of their existence back to nitrogen delivered by storms. Of course, lightning is not the only nitrogen-fixing process on Earth. Certain bacteria in soils and in the roots of legumes perform the same task biologically, using enzymes instead of electricity. But storms have the advantage of scale. They spread nitrates evenly across wide areas, not just around clusters of plants. Every clap of thunder is, in a sense, the sound of the atmosphere recharging the ground with one of life's indispensable ingredients: ozone and the scent of storms. Alongside nitrates, thunderstorms also generate ozone, O3. When lightning splits oxygen molecules, some of the fragments recombine into this triatomic form. Most ozone lives high in the stratosphere, where it shields life from ultraviolet radiation. But during storms, small bursts can form closer to the ground. This is what gives the air that sharp, fresh scent around storms, a tang often described as metallic or electric. Ozone is unstable and breaks down quickly, so the scent is fleeting. But for a moment, it adds to the unique perfume of a thunderstorm. These temporary surges of ozone and nitrates are reminders of how energetic storms truly are. They don't just put on a show, they actively rewrite the chemistry of the sky. For scientists, thunderstorms are laboratories of extreme conditions. They reveal how high-energy events can reshape the air's chemistry, and even hint at how similar processes might unfold on other worlds with lightning-rich atmospheres. On Jupiter and Saturn, with their colossal storm systems, the same reactions could be playing out on a scale far beyond anything seen on Earth. Humans have sensed the fertility of storms for millennia, long before the chemistry was understood. Farmers noticed that crops often looked greener and more vigorous after a series of thunderstorms. The rains didn't just water the fields, they delivered something extra. It took centuries to discover that nitrates were the hidden gift. Ancient myths sometimes imagined thunder as the voice of gods, hurling power and fertility down to the soil. The stories were poetic, but they were rooted in real benefits. Even today, though industrial fertilizers dominate agriculture, thunderstorms still quietly enrich the land. Lightning is estimated to fix between 5 and 20 million tons of nitrogen into usable compounds each year. That may be small compared to human fertilizer production, but it is far from trivial. It ensures that forests, grasslands, and wild ecosystems continue to receive nitrogen without human help. The idea of rain as a delivery system is worth lingering on. Each droplet falling from a storm is more than water, it is a carrier of dissolved gases and nutrients, a chemical message from sky to soil. When these droplets sink into the ground, nitrates spread into the root zone, where plants absorb them to build proteins, enzymes, and DNA. From there, nitrogen moves through food chains, into animals, and eventually back into the atmosphere when organic matter decays. The thunderstorm is a spark that keeps this grand nitrogen cycle turning. There is a paradox here. Thunderstorms often feel chaotic and destructive, roaring winds, blinding flashes, and crashing thunder. Yet out of that violence comes nourishment. The same lightning strike that startles with its power also forges molecules that sustain life. Creation and destruction arrive together, bound in the same flash of energy. So the next time the sky rumbles and rain pours down, it's worth remembering that more is happening than meets the eye. Inside every storm, atoms are being torn apart and recombined. Raindrops are enriched with nutrients, and the soil below is quietly preparing for a burst of growth. A thunderstorm may announce itself with sound and fury, but in its chemistry lies a softer truth. It is one of the planet's oldest gardeners, sprinkling the earth with the ingredients of life. Rain is nature's cleaner. Rain has many talents, but one of its most overlooked roles is that of a cleaner. When clouds finally open and drops begin to fall, they do more than water the ground. Each droplet becomes a tiny janitor of the skies, sweeping up dust, soot, pollen, and even traces of pollution that were floating invisibly above us. The result is a kind of atmospheric house cleaning, one reason the world often feels fresher and clearer after a storm. The process begins before the raindrop even leaves the cloud. As water vapor condenses around microscopic particles, it traps whatever was already suspended in the air: sea salt, smoke, volcanic ash, or industrial emissions. Scientists call this rainout, the capture of particles during droplet formation. In essence, the drop is born already carrying some of the atmosphere's clutter. When it falls, it delivers that package back to the earth, locking the particles into soil or water. The real magic happens on the way down. As raindrops tumble through the sky, they collide with and absorb other particles drifting in the air. This is known as washout. Imagine billions of tiny vacuum cleaners falling from the clouds, sweeping up whatever they touch: dust high above, smoke from chimneys, pollen grains that irritate noses. Gravity and chemistry work together to scrub the air clean. The difference is easy to notice. After a heavy rain, the horizon looks sharper, colors appear more vivid, and the air feels lighter to breathe. This freshness is not an illusion. With fewer particles scattering light, visibility improves dramatically. Fewer pollutants mean less irritation to lungs and sinuses, which partly explains why stepping outside after a storm can feel invigorating. The cleansing effect is especially important in cities, where the air is thick with particles from traffic, construction, and industry, soot from engines, microscopic bits of tire rubber, and dust from building sites. Rain offers a natural reset, temporarily lowering pollution levels and clearing the view. Of course, city rain can be dirtier when it lands, because it gathers pollutants along the way. Puddles may turn gray, and runoff can carry contaminants into drains. But for a brief period, the air above feels renewed. In rural areas, the cleansing is gentler but no less important. Here, the air is often loaded with pollen, spores, and natural dust stirred by winds. Rain presses these irritants back into the soil where they belong. Farmers sometimes welcome rain not just for watering crops, but for clearing the air during heavy pollen seasons. Even forests benefit, as leaves washed by rain are freed of dust, allowing them to breathe more efficiently through their stomata. The chemistry behind this cleaning is elegant. Water molecules are polar, with a slight positive charge on one end and a slight negative charge on the other. This allows them to attract and bind with many different kinds of particles and gases. Some pollutants, like sulfur dioxide and nitrogen oxides, dissolve readily in water, making them easy for raindrops to capture. Others, like dust grains, are simply carried along physically. Either way, the result is the same: less clutter in the air. The scale of this operation is immense. A single rainstorm can remove millions of tons of material from the atmosphere. Air quality measurements often show dramatic drops in particle concentrations after rain, as if nature has flipped a switch, sweeping the skies in one great downpour. This effect is so reliable that researchers sometimes wait for rain events to reset their instruments before taking new readings. The fresh feeling after rain is enhanced by another factor: negative ions. Falling water droplets can break apart and generate these charged particles, which some studies suggest may contribute to the sensation of clean, invigorating air. While the science on their direct health effects is still debated, there's no doubt that freshly washed air feels different, crisp in a way that dry, dusty air never does. Of course, rain's cleaning ability has its limits. In heavily polluted areas, the particles it carries down do not simply vanish, they are transferred to the ground or waterways, where they can create new challenges. But in the moment, the air above is renewed, and the world feels, however briefly, reset. The particles that rain collects don't simply vanish. They accumulate in soils, waterways, and urban infrastructure. Acid rain, in particular, showed how cleaning the air can sometimes shift the problem downward, harming ecosystems and corroding buildings. Rain is an excellent cleanser of skies, but it does not eliminate pollution. It redistributes it. Yet despite this caveat, its role as an atmospheric cleaner is profound. By removing dust that might otherwise block sunlight or clog plant pores, rain shapes ecosystems. By clearing particles that influence how sunlight interacts with the atmosphere, it affects climate. And by reducing fine particulate matter, it improves human health, easing the burden on lungs and hearts. Every shower is, in its own quiet way, an act of maintenance for the planet's atmosphere. There is something poetic about this invisible housework. We see the drops splash on pavements and fields, but above us, each one has already been hard at work, scrubbing, collecting, and restoring balance to the air. The next deep breath you take after a storm is not just psychological relief. It is the taste of cleaner, clearer skies. Rain's chemistry is not always dramatic, but it is unfailingly thorough, washing the heavens so that life below can breathe a little easier. The rainbow's signature. After the rain, the sky often transforms into a canvas. As the clouds begin to part and sunlight returns, a rainbow may stretch across the horizon, as if nature had signed its work with a flourish of color. It feels almost magical. But the secret of the rainbow lies not in mystery, but in physics and chemistry, working together inside countless tiny raindrops. Each droplet acts like a prism, bending and scattering sunlight into its constituent colors. When millions of them shine together, they paint the air with arcs of red, orange, yellow, green, blue, indigo, and violet. The story begins with light itself. Sunlight appears white to our eyes, but it is actually a blend of many wavelengths, each corresponding to a different color. When light passes from one medium to another, from air into water, for example, it bends. This bending is called refraction. It's the same effect that makes a straw look bent in a glass of water, or your legs appear shortened when you stand in a pool. In a raindrop, sunlight refracts as it enters, bending slightly as it slows in the denser medium of water. Inside the droplet, the light reflects off the inner surface, then refracts again as it exits back into the air. This sequence, refraction, internal reflection, and refraction again, turns each raindrop into a tiny projector of color. The key is that each wavelength bends by a slightly different amount. Red light, with its longer wavelength, refracts less sharply than violet light, which has a shorter wavelength. This separation is called dispersion, the spreading of white light into a spectrum of colors. For a rainbow to appear, geometry is crucial. The angle between the incoming sunlight, the droplet, and your eye determines whether the refracted and reflected light reaches you. The most brilliant rainbows occur when the sun is low in the sky, early morning or late afternoon. At these times, sunlight enters raindrops at just the right angle, about 42 degrees for red light, slightly less for violet, to send the spectrum back toward your eyes. This is why you cannot see a rainbow at noon with the sun overhead, the geometry simply doesn't allow it. A rainbow is not a fixed object hanging in the sky, but an optical phenomenon created by countless droplets reflecting light toward you from just the right angles. Move a few steps, and the rainbow you see is technically a different one, built by a new set of droplets. In that sense, a rainbow is personal, a colorful arc tailored to your exact vantage point. Sometimes, a second rainbow appears above the first. This double rainbow forms when light reflects twice inside the raindrop before emerging. With two internal reflections, the geometry changes, and the secondary rainbow appears at a wider angle, about 51 degrees. Because of the extra reflection, its colors are reversed, red on the inner edge, violet on the outer. Double rainbows are fainter because more light is lost with each reflection, but when they appear, they add an extra touch of drama to the sky. Look closely at the inner edge of a bright rainbow, and you may notice a series of faint, closely spaced bands of color. These are called supernumerary bows. Unlike the main arc, which arises from straightforward refraction and reflection, supernumerary bows are born from the wave nature of light. As light waves overlap and interfere inside a droplet, they create additional fringes, delicate pastel bands just inside the primary rainbow. Their presence reveals light's dual personality, part particle, part wave, behaving in ways only physics can fully explain. Raindrops themselves shape much of a rainbow's character. Small droplets tend to produce rainbows that are softer and more pastel, because the dispersion between colors is less distinct. Larger droplets, by contrast, create vivid, sharply defined bands. This is why rainbows after heavy showers often appear more brilliant than those formed by mist. In fog or fine drizzle, rainbows can look pale or ghostly, sometimes called fogbows, with broad white arcs instead of bright colors. The physics of rainbows has fascinated scientists for centuries. Aristotle mused on their geometry, while medieval scholars puzzled over how colors emerge from light. In the 17th century, Isaac Newton famously used a glass prism to show that white light contains the full spectrum of colors, proving that rainbows are not painted in the sky by the heavens, but revealed through the bending of light itself. Yet even with the science laid bare, the sight of a rainbow still evokes wonder. Part of the magic lies in its fleeting nature. It lasts only as long as sunlight strikes droplets at the right angle. A passing cloud, a shift in the sun's position, or a change in rainfall can make it vanish in an instant. That transience adds to its beauty, a reminder that not all spectacles are meant to linger. Across cultures, the rainbow has been a sign of peace, hope, or a bridge between earth and sky. Legends wrapped it in meaning long before anyone spoke of refraction or dispersion. Even now, a rainbow can silence conversation as people stop to gaze upward. Science may explain the mechanics, but it does not diminish the sense of wonder. Every rainbow you see is the work of millions of raindrops, each one a lens and a mirror, splitting sunlight into its hidden colors. Together, they weave a grand arc across the sky, a chorus of physics and chemistry made visible. The next time sunlight and rain meet at just the right moment, pause to watch the spectacle unfold, knowing that within each shimmering band lies a lesson in the quiet power of water and light. Raindrops as couriers of Earth's minerals. Every raindrop begins its life as more than just water. To condense it all, vapor needs a speck to cling to, a nucleus around which it can gather. These seeds are usually tiny fragments drifting in the air, grains of dust, crystals of sea salt, microscopic bits of volcanic ash, or even pollen. While they may seem insignificant, these particles shape the chemistry of rain and, in turn, influence the world below. Each falling drop is not simply liquid from the sky, but a courier carrying minerals and elements across the planet's surface. Consider dust. Winds sweep across deserts and dry plains, lifting fine particles high into the atmosphere. The Sahara Desert, for example, is a vast supplier of airborne dust, sending plumes thousands of kilometers across oceans. When raindrops form around this dust, they capture its mineral load, and when they fall, they deliver it to faraway ecosystems. This is no minor contribution. Dust from the Sahara feeds soils in the Amazon rainforest, replenishing nutrients lost to heavy rains and rapid plant growth. The cycle links continents, with raindrops as the go-betweens. sea salt plays an equally important role. When waves break, they fling tiny droplets of seawater into the air. These droplets dry, leaving behind crystals of salt that drift upward, waiting for moisture to gather. Raindrops forming on these salty seeds carry a faint briny signature. Over oceans, this process is constant, ensuring marine air is rich with salt particles. When rain falls back into the sea, the chemistry is recycled. But when salt-laden rain drifts inland, it can deliver sodium, chloride, and other ions to soils far from the shore, a gentle seasoning that benefits plants and ecosystems, though too much salt can be harmful. Volcanic ash adds yet another ingredient. During eruptions, volcanoes release not only dramatic clouds of smoke, but also enormous amounts of fine ash and mineral-rich dust. Lofted into the stratosphere, these particles can remain aloft for months or even years, seeding raindrops across the globe. The minerals they carry, silica, iron, calcium, potassium, enrich soils, making volcanic regions some of the most fertile on Earth. Farmers living near volcanoes may dread eruptions for their danger, but they also know that the ash eventually blesses the land with extraordinary fertility, often delivered through rain. The chemical fingerprint of rain. All of this means that raindrops are not chemically identical everywhere. Rain falling over oceans tends to be slightly salty, carrying traces of marine aerosols. Rain sweeping across deserts may hold alkaline minerals like calcium carbonate, making it less acidic than normal. In forested regions, rain may carry organic compounds from plant emissions. Each shower has its own chemical fingerprint, a reflection of the particles it encountered on its journey from vapor to liquid. The impact on soil fertility is profound. Nitrates from thunderstorms fertilize crops. Dust minerals support lush forests. Even trace elements like iron, delivered in Saharan dust, can stimulate plankton blooms in distant oceans. It's easy to imagine each raindrop as a tiny courier traveling from sky to earth with a package of minerals tucked inside. Some carry a pinch of desert dust, others a crystal of sea salt, others a fragment of volcanic glass. Released by the fall, these small gifts scatter into soils, rivers, and oceans, feeding cycles that sustain life. Individually, the cargo seems trivial. Collectively, over billions of drops, it is a delivery system on a planetary scale. The chemistry also affects how rain feels and smells. Sea salt rain can have a crisp freshness that inland rains lack. Dust-rich rain can alter pH, making it more alkaline than the mild acidity caused by carbon dioxide alone. In some regions, people notice mud rain, when Saharan dust or other particles are so abundant that raindrops fall visibly stained with soil. Cars, windows, and laundry left outside may be speckled with reddish or brown spots, visible proof that the sky has been carrying cargo across continents. A planet connected by rain. The long-distance transport of minerals through rain is a reminder of how interconnected the Earth really is. A shower in the Amazon may owe some of its nutrients to winds in Africa. Crops in Europe may receive salts born of waves in the Atlantic. Even the clarity of a remote mountain lake can be influenced by volcanic ash deposited halfway around the world. What seems like a local rainstorm is often tied to processes that span thousands of kilometers. This mineral delivery is not always beneficial. Alongside natural dust and salt, raindrops can also carry pollutants, heavy metals, soot, or chemical residues from human activity. These too become part of the raindrop's cargo, with less friendly consequences for ecosystems. Yet the principle remains the same: every droplet is a vehicle carrying more than just water, redistributing whatever the atmosphere provides. The sky is not just a reservoir of water, but a network of couriers dispatching millions of tiny packages to the ground below. Some of those packages feed forests and oceans. Others carry reminders of distant deserts or restless volcanoes. Together, they ensure that Earth's chemistry remains dynamic, that no ecosystem is ever entirely cut off from the rest. Every drop that splashes onto a leaf or trickles into the soil carries a story written in dust, salt, and minerals. Raindrops are more than water. They are messengers, delivering fragments of Earth back to Earth, ensuring that life continues to be nourished far from where those fragments began. The water cycle, deep time, and rain is life's first chemist. At its heart, the water cycle is pure chemistry, the shifting bonds between molecules, the dissolving of gases, the constant interplay between liquid, vapor, and ice. Rain is one of its most visible stages, but the journey of water is vast, ancient, and endlessly repeated. It begins with evaporation, driven by the sun's energy. At the surface of oceans, rivers, and lakes, water molecules gain enough energy to break free from their liquid neighbors and rise as vapor into the atmosphere. Each escaping molecule is part of a collective migration. Vast amounts of water vapor are lifted every day, especially from warm seas, yet we hardly notice it happening. Even in colder regions, evaporation ticks away slowly, powered by the sun's steady hand. Alongside evaporation, plants contribute through transpiration, releasing water vapor from their leaves during photosynthesis and respiration. Together, these processes feed the skies with an invisible reservoir. As this vapor rises, it cools. Molecules moving at high speed slow down in the thinner, colder air of higher altitudes. Cooling encourages condensation, vapor returning to liquid form. With the help of dust, salt, or other airborne particles, water molecules cluster into droplets. When enough droplets gather, they form clouds, great visible symbols of the cycle in motion. To the eye, a cloud may look light and fluffy, but in truth, it holds massive amounts of water suspended above the ground. Eventually, the balance tips. Droplets collide and merge, growing heavy enough that rising air currents can no longer support them. Gravity takes hold, and precipitation begins, falling as rain, or, depending on temperature, as snow, sleet, or hail. Each drop or crystal is a small delivery, carrying water back to the Earth's surface in a ceaseless exchange. Water across deep time. What makes this cycle remarkable is that it has been happening for billions of years. Many of the water molecules in a glass you drink, or in the raindrops sliding down a window, have been circulating since the earliest days of the planet. Some may have fallen as rain on ancient forests when dinosaurs roamed. Others may have frozen into glaciers, locked away for millennia before melting and rejoining the flow. A single molecule might have spent centuries drifting in the ocean before evaporating again, a traveler on a grand looping journey. This recycling is so complete that no new water is truly made or lost on Earth. The water we use today is the same that once coursed through prehistoric rivers, filled primeval seas, and formed ice in ancient polar caps. When rain falls, it is not the birth of new water, but the return of old companions, endlessly reshuffled. Perhaps this is why rain feels refreshing. Each drop is both present and ancient, a reminder of continuity across unimaginable spans of time. The cycle's chemistry and climate role. Rainfall links the parts of the cycle together. From the ocean, water vapor rises, condenses, and returns as rain, replenishing rivers and lakes. From glaciers, melting ice feeds streams that join those rivers, their waters eventually returning to the sea. Groundwater, too, plays its role, absorbing rain that seeps into soils and aquifers, only to resurface through springs or wells. Nothing is wasted. Every pathway leads back into the cycle, even if the journey takes thousands of years. Chemistry shapes each stage. The polarity of water molecules, with their slight positive and negative charges, allows them to bond and unbond with ease, moving between states with small changes in energy. The dissolving of carbon dioxide in rain gives it a mild acidity, helping it weather rocks and release minerals into rivers. The freezing and melting of ice depend on hydrogen bonds that form crystalline lattices, making ice less dense than liquid water, a rare property in nature. Without these quirks of chemistry, the water cycle would look very different. The cycle also acts as Earth's climate regulator. As water evaporates, it carries heat away, cooling surfaces. When it condenses into clouds and rain, it releases that stored heat into the atmosphere, driving weather systems and distributing energy across the globe. Rain is not just a local event, it is part of a planetary system of balance, transporting heat as well as water from one region to another. Raindrops as time travelers. There is a poetic truth in recognizing that every raindrop carries an ancient memory. When it splashes onto your hand, you are touching water that may once have rolled off the back of a mammoth, trickled through a canyon in its youth, or lain frozen deep inside a glacier for tens of thousands of years. Some of it may even predate Earth itself, arriving on icy comets that bombarded the young planet and helped fill its oceans. To think of a raindrop in this way is to see it not as fleeting moisture, but as a traveler across deep time. The global water cycle is both relentless and delicate, relentless because it never stops moving water between sky, land, and sea, delicate because small shifts in temperature, air currents, or chemistry can alter its rhythm, changing where rain falls and where drought lingers. For life on Earth, the cycle is not background, it is the foundation. Crops depend on predictable rainfall. Rivers carve landscapes. Oceans circulate heat. And through it all, the chemistry of water molecules binds the cycle together. Rain is the visible signature of this grand process, the moment when the sky gives back what it borrowed. In each falling drop is the essence of a journey that spans continents, oceans, and ages. It is chemistry in motion, carrying not only the freshness of the present, but also whispers of the past. Rain and the origins of life. The rain we experience today nourishes crops, washes the air, and fills rivers. But long ago, it may have done something even more remarkable, it may have helped spark life itself. Billions of years ago, when the young Earth was a restless and stormy world, rain fell not onto fields and forests, but onto bare rock and steaming volcanic plains. Into these early pools and puddles, raindrops may have delivered the raw ingredients that eventually built living cells. One idea is that rain brought essential molecules from the sky to the ground, concentrating them in small places where they could interact. The early atmosphere was very different from today's, thick with methane, ammonia, hydrogen, and water vapor. Volcanoes added carbon dioxide and sulfur compounds. Without the stabilizing influence of plants or an oxygen-rich atmosphere, storms were frequent and violent. Lightning forked through the skies constantly, splitting molecules apart and allowing them to recombine in novel ways. When rain fell, it swept these new products into pools and puddles, liquid laboratories on the Earth's surface. In the 1950s, an influential experiment by Stanley Miller and Harold Urey offered a clue. They recreated what they believed the early Earth's atmosphere might have been like, filling a closed system with methane, ammonia, hydrogen, and water vapor, then zapping it repeatedly with electrical sparks to mimic lightning. After a week, the water at the bottom of their apparatus had turned brown. Analysis revealed amino acids, the fundamental building blocks of proteins. The implication was astonishing: lightning and rain, working together in the right atmosphere, could spontaneously create the ingredients of life. The experiment was not a complete recipe for life, but it demonstrated an important principle: energy from lightning and chemistry from rainfall could generate complexity out of simplicity. Once deposited into ponds and pools, these amino acids and other organic molecules might have accumulated further, forming rich chemical soups. In shallow waters, where evaporation could concentrate them even more, they might have linked into chains, laying the groundwork for proteins, nucleic acids, and eventually self-replicating systems. In this way, rain was not just a delivery system, but a concentrator and stage setter, making conditions ripe for further steps toward life. Water is an ideal medium for chemistry, allowing molecules to bump into one another, react, and disperse. But water alone can also dilute things too much, spreading molecules so thin that reactions struggle to happen. Rain as life's midwife and the plant's silent partner. Rain, by filling small pools and then drying partially under the sun, could have created natural cycles of concentration and dilution. These wet-dry cycles are thought to be crucial for forming long molecular chains like RNA or DNA. In essence, rain may have stirred the pot, drying and refilling primitive ponds until complexity began to emerge. Not all scientists agree on the exact details. Some suggest life may have begun not in surface puddles, but deep at hydrothermal vents in the ocean. Others point to icy environments, or even the delivery of organic molecules by comets. Yet even in these scenarios, rain may still have played a supporting role, shaping the atmosphere and distributing materials across the planet. The beauty of the water cycle is that it connects everything: ocean, land, and sky. Wherever the ingredients for life appeared, rain would have been one of the forces moving them into place. It's worth imagining what those first rains must have been like. The young earth lacked the forests and fields we know today. Instead, rain fell onto bare rock, into volcanic craters, and across landscapes of shallow seas. Every storm may have been a chemical experiment, mixing gases, minerals, and energy into unpredictable results. The smell of those rains would not have been the comforting petrichor we know, but likely sharp and acrid with sulfur and ammonia. Yet within that alien atmosphere, droplets were carrying the seeds of something entirely new. Rain beyond Earth. This perspective even extends beyond our own world. Could alien planets also experience rain chemistry? On Titan, Saturn's largest moon, rain falls not as water, but as liquid methane. While this does not support life as we know it, it shows that rain is a universal process wherever an atmosphere and liquid coexist. On Venus, droplets of sulfuric acid fall through thick clouds, though they evaporate before reaching the surface. On distant exoplanets, astronomers believe it might even rain molten iron, glass, or exotic hydrocarbons. If rain on Earth helped build life, it is tempting to wonder whether rains on other worlds might play similar creative roles, albeit with very different ingredients. The midwife of life. The story of rain and life's beginnings is not one of certainty, but of possibility. Each drop falling onto the young planet carried gases from the sky, minerals from volcanic eruptions, and the electrical energy of storms. Together, these contributions may have nudged chemistry toward biology, from molecules toward metabolism, from chance reactions toward the first fragile cells. Life did not appear in an instant. It was coaxed into being by countless interactions, many of them happening in water delivered from the clouds above. To think of rain in this way is to give it a new kind of significance. Today, it fills rivers, nourishes plants, and cleans the air. But in the deep past, it may have been one of the midwives of life itself, each falling drop a tiny experiment, a carrier of possibility, an agent of transformation. When you feel rain on your skin, you are touching not just water, but a reminder of those ancient days when the first whispers of life might have been written into puddles by storm and sky. Rain and the plant's dialogue. When rain falls on a field, a forest, or even a potted plant on a windowsill, it is easy to think of it as simple hydration: water in, plants grow. End of story. But in truth, every shower is a kind of chemical conversation between sky and soil, droplets and leaves. Rain brings more than moisture, it carries dissolved gases, nutrients, and even signals that plants interpret in surprising ways. One of the most important chemical gifts rain provides is nitrogen in a usable form. The atmosphere is rich with nitrogen gas, but it is locked away as N2, a molecule so stable that plants cannot break it apart themselves. Rainstorms, particularly those accompanied by lightning, perform the difficult work of splitting nitrogen atoms and binding them with oxygen to form nitrates. These nitrates dissolve into raindrops and descend to the earth, sinking into the soil. For plants, nitrates are gold, the raw material for amino acids, proteins, and nucleic acids. Every leaf, stem, and seed relies on nitrogen, and rainfall is one of the quiet couriers delivering it. Alongside nitrogen, rain also carries dissolved carbon dioxide. As droplets fall through the air, they absorb CO2, forming a weak solution of carbonic acid. Though mild, this enriches the soil with carbonates that plants and microbes can use. In some cases, carbon dioxide in raindrops also helps buffer soil chemistry, balancing acidity and keeping nutrient cycles steady. Even oxygen from the atmosphere finds its way into rainfall. As raindrops splash onto soil and seep downward, they carry small amounts of dissolved oxygen, helping to aerate the upper layers of earth where roots spread. Rain's physical care for plants. The benefits of rain extend beyond chemistry. Rain washes leaves, clearing them of dust, pollen, and pollutants that accumulate during dry spells. A plant's leaves are its solar panels, converting light into energy through photosynthesis. Dust on their surfaces can reduce efficiency, shading them from sunlight and clogging the tiny pores called stomata. A good rain is like a thorough cleaning service, restoring leaves to full working order. Afterward, the canopy often looks brighter and greener, not only because of the water's shine, but because the leaves are newly polished for their work. Rain also influences the balance of moisture in the soil. Roots depend on a delicate ratio of water and air in the spaces between soil particles. Too little water, and roots struggle to absorb nutrients. Too much, and oxygen is pushed out, suffocating them. Gentle rains are particularly effective at soaking into the ground, replenishing water without overwhelming root systems. Heavy downpours can be less ideal, sometimes compacting soils or causing runoff that carries nutrients away. Yet even then, the cycle is reset, and life continues its negotiation between abundance and scarcity. Plants responding to rain. Plants are far from passive in this relationship. They have evolved ways to respond chemically to rainfall. Some species release hormones that trigger rapid growth after soaking. Desert plants, for example, may remain dormant for months, then burst into bloom following a rainstorm, responding to the sudden availability of water and nutrients. In agriculture, farmers sometimes notice crops visibly perk up within hours of rain, not just because of water, but because of this internal chemistry of response. Seeds, too, can be attuned to rain. The earthy fragrance we call petrichor is partly produced by oils secreted by plants during dry spells. These oils accumulate in soil and rock, lying dormant until rain releases them into the air. But petrichor is not merely a perfume for humans, it may act as a chemical signal to seeds waiting in the soil. For some species, these compounds announce that rain has arrived and conditions are finally right for germination. Seeds that might otherwise remain dormant for years can sense the shift and awaken, sprouting into new life. Rain's dialogue with plants and the sea. Rain carries a chemical message across generations of plants. Now is the time to grow. There is a subtle choreography in the way plants respond to moisture at both their leaves and roots. Stomata, the tiny openings on leaf surfaces, often close during dry weather to conserve water. When rain arrives and soils are replenished, plants can afford to open them wider. This not only allows carbon dioxide to flood in for photosynthesis, but also permits transpiration, the release of water vapor that cools the leaf. A fresh rain resets the balance, allowing the plant to breathe more freely. Rain's chemical conversation with plants extends far beyond the individual. When it delivers nitrates and other nutrients, plants grow more vigorously, producing more leaves and stems. These, in turn, release more oxygen into the atmosphere. Healthier plants support herbivores, which support carnivores, sending ripples through entire ecosystems. The chemistry of a single shower can cascade outward, influencing the rhythm of a forest or the productivity of a meadow. Human agriculture has long depended on this interplay. Before synthetic fertilizers, farmers relied heavily on the natural fertilization provided by rain. Even today, rainwater often contains a more balanced mix of nutrients and fewer salts than irrigation water, making it particularly beneficial for crops. Gardeners often remark that plants look greener and healthier after a rain compared to artificial watering, and science supports this. The combination of dissolved gases, nitrates, and the physical washing effect makes rainwater unique. It is easy to think of rain as simple hydration. But for plants, it is more like a full conversation, one that involves nutrients, cleaning, hormonal responses, and even signals for seeds to awaken. Every drop that falls onto a leaf or seeps into the soil carries more than moisture. It carries information and sustenance, messages written in the language of chemistry. The next time rain freshens a garden or forest, imagine the quiet dialogue taking place: nitrogen forged by lightning slipping into roots, dust rinsed from leaves, seeds beneath the soil sensing chemical cues that tell them to stir. Rain may seem like an ordinary part of weather, but for plants, it is a partner, a messenger, and a catalyst, engaging them in a conversation that has continued for hundreds of millions of years. When rain meets the ocean. When rain falls over the ocean, it enters a world already dominated by water. At first glance, it may seem like a small and redundant act, adding fresh droplets to an endless salty expanse. Yet the chemistry of those raindrops matters more than it might appear. They create subtle but important changes at the ocean's surface, influencing salinity, nutrient mixing, and even the behavior of microscopic life. The ocean is salty because of minerals carried into it by rivers over millions of years. Sodium and chloride are the most abundant, but magnesium, calcium, potassium, and sulfate also contribute to its chemistry. On average, seawater contains about 35 g of dissolved salts per liter, a balance marine life has adapted to with exquisite precision. Rainwater, by contrast, is fresh. When it falls onto the ocean, it creates a temporary layer of lower salinity at the surface. This dilution is often only a few centimeters thick, but for organisms living in the delicate boundary between air and sea, it can make all the difference. This surface layer is called a lens of freshened water. It floats because fresh water is less dense than salt water, and it can persist for hours or even days depending on winds and currents. The sudden reduction in salinity affects the way gases exchange between ocean and atmosphere. A freshened surface can change how easily carbon dioxide dissolves into the sea, or how oxygen moves out. Rain is therefore not just watering the ocean, it is actively altering the chemical interface through which gases pass. Raindrops also deliver their own chemical passengers. As they fall, They collect gases such as carbon dioxide, nitrogen oxides, and sulfur compounds from the atmosphere. They may also carry tiny particles of dust, pollen, or sea salt that seeded their formation. When these drops meet the sea, they deliver this cargo to the surface waters, a subtle but constant infusion linking atmosphere and ocean in a chemical dialogue that keeps marine systems alive and dynamic. When precipitation freezes before reaching the ground, it can take on dramatically different forms. Hail falls as small pellets or, in extreme cases, as golf ball-sized or even larger missiles of ice. Slice a hailstone open and you'll often see concentric layers, like the rings of a tree, recording its repeated journeys up and down through the storm before gravity finally wins. Snow, in contrast, forms more gently. At its heart lies the unique geometry of water molecules, two hydrogen atoms bonded to one oxygen atom in a bent shape, with slight positive and negative charges. When water freezes, these charges encourage the molecules to lock together in a hexagonal pattern. This is why snowflakes almost always display six-sided symmetry. As a crystal grows within a cold cloud, water vapor condenses onto it, extending branches outward. Tiny changes in temperature and humidity along the way influence the exact form, producing an astonishing diversity of shapes. Some snowflakes resemble delicate stars, others needles or plates, but all follow the same hexagonal blueprint. Snow's chemistry is also distinct from rain. As flakes fall, they trap pockets of air, dust, and sometimes even atmospheric pollutants. Each crystal is a tiny time capsule, recording the conditions of the cloud from which it formed. In polar regions, snow accumulates year after year, compressing into ice sheets that preserve ancient atmospheres in microscopic bubbles. By analyzing these bubbles, scientists can reconstruct climate history stretching back hundreds of thousands of years. Freezing rain is yet another variation, and one of the most dangerous. It begins as ordinary raindrops falling through a layer of warm air, melting any ice crystals into liquid. But as the drops descend, they pass through a shallow layer of sub-freezing air near the ground. The droplets remain liquid, supercooled, until they strike a surface, where they freeze instantly into a smooth coating of ice. The result is an ice storm, glazing trees, power lines, and roads in treacherous, glassy armor. Chemistry in crystal form. The differences between hail, snow, and freezing rain highlight water's versatility. In hail, the story is one of layering and rapid freezing upon contact with supercooled droplets. In snow, it is molecular geometry expressed in elegant crystal patterns. In freezing rain, it is the precarious balance between liquid and solid states, determined by thin slices of temperature in the atmosphere. Small variations in conditions can create entirely different outcomes from the same H2O molecules. From a practical standpoint, these frozen forms shape ecosystems and human life. Snow blankets the ground, insulating plants and animals while slowly releasing water during the spring melt. Its mild acidity from dissolved carbon dioxide contributes to soil weathering and nutrient cycling. Hail can devastate crops, shredding leaves and bruising fruit in minutes. Freezing rain challenges infrastructure, snapping power lines under its weight and turning roads into sheets of ice. Culturally, frozen precipitation has inspired both wonder and caution. Snow has long been celebrated for its beauty, each flake a crystalline work of art. Hail has been feared since ancient times, often interpreted as a sign of divine anger. Freezing rain, less poetic but no less dramatic, reshapes landscapes overnight, coating branches and fences in gleaming ice as though the world has been dipped in glass. What unites them is the same fundamental chemistry, the polar nature of water molecules, their tendency to bond into patterns, and their responsiveness to temperature shifts. From the softness of falling snow to the violence of hailstones and the treachery of ice storms, all are expressions of water's simple but endlessly adaptable formula. When we watch flakes drift, hear hail rattle against rooftops, or see trees bowed under the glaze of an ice storm, we are witnessing chemistry in crystal form, water transformed by the air it passes through, becoming architect, sculptor, and sometimes adversary. Rain as a reflection of place. A raindrop is never just water. It is a traveler, shaped by the air it passes through and the particles it encounters. Nowhere is this contrast clearer than in the difference between rain that falls in bustling cities and rain that falls in quiet forests. At first glance, the drops may look identical, but chemistry tells a different story. In cities, the air is crowded. Vehicles release nitrogen oxides, carbon monoxide, and fine particles from exhaust. Buildings shed dust, while construction projects add cement particles and microscopic debris. Industrial processes contribute sulfur dioxide and volatile organic compounds. Even the everyday wear of tires and brakes releases invisible fragments into the air. A raindrop forming or falling through this atmosphere cannot help but absorb some of it. By the time it reaches the pavement, it is often more acidic and chemically complex than drops falling in remote countryside. City rain often contains higher concentrations of sulfuric and nitric acids, formed when raindrops capture sulfur dioxide and nitrogen oxides from traffic and industry. The result is rain with a pH lower than the mild 5.6 typical of natural rainfall. This sharper chemistry can corrode stone, etch glass, and stress plants growing in urban soils. For centuries, city buildings, from marble statues to limestone facades, have borne the scars of acidic precipitation, their features softened and details blurred by rain harsher than nature intended. In forests, the air is filled not with soot and exhaust, but with biological aerosols. Trees release a cocktail of organic compounds, terpenes from pines, isoprene from broadleaf species, and countless other plant volatiles. These molecules, far from pollutants, are part of the natural conversation between plants and atmosphere. They act as cloud condensation nuclei, giving water vapor something to gather around. As a result, forest rain often carries traces of these compounds, giving it a chemistry that is softer, more neutral, and sometimes faintly nourishing. Forest canopies also add to the cleansing power of rain. As drops fall through layers of leaves and branches, they are filtered and sometimes enriched. Leaves capture dust and pollen, washing them down to the soil. In doing so, rain falling in forests often removes particles from the air more effectively than city showers, leaving the post-rain atmosphere feeling unusually fresh. Forest freshness, urban grit, and the future chemistry of rain. Anyone who has stepped into a woodland after rainfall knows the clarity of the air and the distinctive earthy perfume, petrichor, intensified by plant oils and the microbial compound chiasmin. This is not just an illusion of freshness. It is chemistry that quite literally makes the air cleaner. There is evidence that forest rains can even alter soil chemistry in beneficial ways. Organic acids washed from leaves and bark enrich the upper soil layers, influencing microbial communities and nutrient cycles. By contrast, city rain, with its acidity and pollutants, can leach nutrients from soils, stressing urban vegetation. This difference partly explains why plants thrive so vigorously in natural settings compared to the same species struggling in a roadside planter. The rain that nourishes them is chemically different. The contrast between city and forest raindrops is visible as well as measurable. Rain in forests is usually crystal clear, while urban rain can leave behind residues. After a storm in a large city, cars and windows may be dotted with faint films of soot or grime, evidence of what those droplets carried down. In heavily polluted areas, residents even report dirty rain that streaks clothing and buildings. One might say, with a touch of humor, that city raindrops sometimes need a chemical bath themselves before they can be considered clean. Beyond these visible differences, rain chemistry shapes broader environmental systems. In urban areas, acidic rainfall accelerates the weathering of infrastructure, increasing maintenance costs for bridges, statues, and historic landmarks. It also burdens stormwater systems, as runoff carries collected pollutants into rivers and lakes. In forests, rain contributes to nutrient recycling, washing fallen leaves into soils and feeding roots with dissolved minerals. It sustains biodiversity, maintaining delicate balances between soil, microbes, fungi, and plant roots. Even the way raindrops form is influenced by their environment. Cities, with their higher concentrations of aerosols, often produce more numerous but smaller droplets, leading to misty rains. Forests, with fewer but more organic nuclei, tend to form larger droplets that fall more heavily, creating a different rhythm and sound. The patter of rain on leaves is softer and more diffuse than the sharp percussion of drops on asphalt, a sensory reminder of the chemistry at play. Forests can even generate their own rainfall. Through transpiration, trees release vast amounts of water vapor, feeding cloud formation overhead. The organic aerosols they emit act as condensation seeds, further promoting cloud development. The rain that follows is, in a sense, the forest calling water back to itself. Cities, by contrast, often disrupt rainfall patterns. Heat islands alter convection currents, and polluted aerosols modify cloud behavior. Urban areas may experience either suppressed rainfall or sudden, intense downpours, both tied to their unique atmospheric chemistry. From a human perspective, the difference is as much felt as measured. Walking through a city in a downpour can feel gritty, the rain carrying the tang of exhaust or industrial air. Stepping into a forest shower feels rejuvenating, the drops cooler, the air cleaner, the scents invigorating. Both are rain, but they are rain shaped by their journeys, one touched by engines and smoke, the other by leaves and soil. At its core, this contrast reminds us that raindrops are not independent of us. They fall through the world we create and carry pieces of it with them. Cleaner skies lead to cleaner rain, whether above a city or a forest. Forests, with their ability to generate their own refreshing chemistry, offer a kind of template for balance, air filled with organic compounds that seed clouds, rain that nourishes rather than corrodes, and cycles that sustain rather than erode. Every raindrop is a chemical story written on its way down. In cities, it tells of cars, chimneys, and concrete. In forests, it whispers of leaves, soil, and ancient biological rhythms. The water molecule, H2O, is the same, but its companions change everything. To stand in either downpour is to feel the difference between human-made skies and nature's green chemistry. Rain has always been a familiar companion, a cycle as old as the planet itself. Yet the chemistry of raindrops is not fixed in time. It shifts with the atmosphere, reflecting the gases, particles, and energy above our heads. As the climate changes, so too will the composition of rain. The drops that fall a century from now may carry signatures different from those we know today, a reminder that rain is not timeless in its chemistry, even if it feels eternal in its rhythm. One of the clearest ways climate change influences rain chemistry is through alterations in acidity. Natural rainfall is mildly acidic, with a pH of about 5.6 due to dissolved carbon dioxide forming carbonic acid. In the 20th century, industrial emissions of sulfur dioxide and nitrogen oxides created widespread acid rain, scarring forests and lakes. Regulations in many countries curbed these pollutants, and rainfall in those regions gradually recovered. But climate change introduces new dynamics. Warming temperatures and shifting circulation patterns redistribute pollutants, affecting where and how strongly acidity emerges. Regions that once had neutral or slightly alkaline rains may find their precipitation turning sharper, while others may experience a dilution of acidity due to changing winds and rainfall intensity. Particulates now play a growing role. Wildfires, intensified by rising global temperatures, release massive amounts of soot, ash, and organic aerosols into the atmosphere. These particles seed raindrops, altering not only their frequency but also their chemistry. Rain falling through smoke-laden skies carries a different profile, infused with carbon compounds and trace metals. The same is true for dust. Desertification in some regions increases airborne minerals, shifting rainfall toward greater alkalinity. In this way, climate change sculpts rainfall chemistry through both fire and drought, adding new layers to the familiar cycle. Ozone is another factor. Tropospheric ozone, the ozone near the ground, distinct from the protective stratospheric layer, is increasing in many regions due to rising emissions of volatile organic compounds and nitrogen oxides, combined with warming temperatures. Ozone itself is not especially soluble in water, but it reacts with raindrops during storms, contributing to the sharp scent often noticed in thunderstorms. As ozone levels shift, the chemical fingerprint of storm rain may shift as well. The fragrance of a summer thunderstorm, that electric tang in the air, could subtly change as atmospheric chemistry evolves. Scientists are also exploring geoengineering, deliberate attempts to alter the atmosphere to counteract climate change. Some proposals involve injecting aerosols into the upper atmosphere to reflect sunlight, mimicking the cooling effect of volcanic eruptions. If implemented, such interventions would inevitably alter rainfall chemistry. Raindrops forming in skies seeded with engineered particles would differ from those formed naturally, in acidity, mineral content, and even their role in cloud dynamics. Cloud seeding, already practiced in some regions, uses silver iodide or other substances to encourage rainfall. Scaling this up could redefine rainfall as an engineered event, shaped as much by human hands as by natural cycles. These possibilities raise open questions about the sensory experience of rain in the future. One of its most cherished qualities is its smell, petrichor, the earthy fragrance released when drops strike dry ground, and the ozone-tinged scent of storms. Will these endure? If rain chemistry shifts, they might change subtly, perhaps imperceptibly at first. Drier soils may produce different aromatic oils. Shifts in microbial communities could alter the geosmin that gives rain its earthy character. Future generations may even associate rainfall with entirely new scents linked to altered atmospheric compounds. What feels timeless to us today may evolve alongside the planet's chemistry. And as climate change reshapes rainfall patterns, intensifying it in some regions while reducing it in others, the story of rain will continue to be rewritten in the language of molecules. Rain's future, its poetry, and its continuity. In wetter regions, heavier downpours could wash greater amounts of pollutants and nutrients into soils and rivers, amplifying rain's role as a chemical delivery system. In drier regions, rarer rains may carry heavier chemical loads, having absorbed more dust and particulates during their long absence. Rainfall may grow more extreme in both chemistry and frequency, reflecting a less stable climate. Despite these uncertainties, there is reason to hope that rain can remain both purifier and mirror. Efforts to reduce emissions have already shown that rain chemistry can improve within decades. The reduction of acid rain in Europe and North America demonstrates how quickly the atmosphere can respond when pollutants are cut back. Expanding such efforts globally could ensure that rain in the future is cleaner, even as the climate changes. Cleaner technologies, reduced reliance on fossil fuels, and better air quality management could mean raindrops once again fall closer to their natural chemistry, carrying little more than carbon dioxide and natural aerosols. What rain will always retain is its central role in connecting atmosphere and earth. Whether carrying soot, dust, nitrates, or plant oils, raindrops embody the chemistry of their time. To study them is to read the story of the skies above, written in molecules and ions. The future may bring sharper acidity in some places, greater alkalinity in others, and new signatures of fire and smoke. But the rain itself will remain the bridge. It will always fall, always cleanse, always renew, even if its exact chemistry evolves. There is something reassuring in this continuity. While we may debate whether tomorrow's rain will smell the same, or whether geoengineering will alter its profile, the fundamental rhythm of the water cycle endures: evaporation, condensation, precipitation. These steps have turned endlessly for billions of years, and they will continue. What changes is what rides within those drops, the invisible chemistry shaped by both natural forces and human choices. Perhaps the most important reflection is this: rain in the future will be what we make of it. If we fill the skies with soot and smog, raindrops will dutifully carry them back down. If we clean the air, they will return with clarity. If we tinker with the atmosphere, rain will adjust accordingly. The chemistry of tomorrow's rain is not pre-written, it is the outcome of today's actions. And within every drop lies a reminder that the future of rain is bound to the future of the planet itself. Rain is chemistry, yes, but it is also something far more intimate: rhythm against rooftops, the hush of falling drops in a forest, the soft percussion on a windowpane as night draws near. Each raindrop is a cluster of molecules obeying the rules of physics and chemistry, yet to our senses it feels like music. It is the world breathing, the sky reaching down, the steady pulse of the water cycle expressed in sound and touch. To think of rain only as water would be to miss its poetry. Every falling drop carries both order and randomness. On the molecular level, water molecules align through hydrogen bonds, their polarity pulling them together into spherical forms. The geometry of oxygen and hydrogen, set by quantum mechanics, dictates the curves and cohesion of each drop. Yet on the ground, the rain arrives in patterns that feel anything but orderly, splashing, gathering, running into rivulets, creating puddles that reflect the sky. Science explains how raindrops form and fall, but our senses interpret them as something gentler, a lullaby written by clouds. Rain also connects us to time itself. The water that falls today has been here for billions of years, reshuffled again and again. A raindrop sliding down glass might once have been frozen in a glacier, coursed through a dinosaur's bloodstream, or risen as vapor from a prehistoric sea. This continuity is one of the quiet marvels of rain, both immediate and ancient, refreshingly new and unimaginably old. When we listen to rainfall, we are hearing the echoes of ages past, molecules returning from journeys we can barely comprehend. The comfort of rain may lie partly in its chemistry. Petrichor, that earthy fragrance after rain, is a molecular message: plant oils, microbial geosmin, and the sharp tang of ozone mingling in the air. These scents trigger something deep in us: associations with fertility, renewal, and safety. Our ancestors, dependent on rainfall for crops, would have felt relief at its arrival, and perhaps our bodies still remember. What begins as a reaction between molecules and water becomes, for us, nostalgia and calm. Yet rain is not just a messenger of peace, it is also a sculptor. Chemically mild though it seems, its faint acidity weathers stone, dissolving minerals grain by grain, shaping valleys, canyons, and caves. Each drop participates in the slow art of erosion, carving landscapes over millennia. When rain seeps into soil, it dissolves and carries nutrients, redistributing life's raw materials. Its chemistry writes on the land in the long hand of time, even as its rhythm soothes us in the moment. There is a duality in rain, both scientific and poetic, both explanation and experience. Knowing that lightning splits nitrogen molecules in the sky, forming nitrates that fertilize the ground, does not make a thunderstorm less magical. Understanding that rainbows arise from refraction and reflection within droplets does not diminish their wonder. In fact, the more one learns about rain's chemistry, the more remarkable it becomes. The molecules fall whether we notice or not, but when we do, we see both the invisible bonds and the visible beauty. Listen closely, and rain reveals itself as music. Each surface it touches plays a different note, leaves whisper, roofs drum, windows patter, puddles echo with hollow plinks. To our ears, this randomness organizes itself into rhythm. Scientists might call it stochastic distribution, but we hear it as melody. In this way, rain is like a language spoken by nature, one that speaks through both chemistry and sound. It invites stillness. Its steady fall narrows the world, muting distant noises, drawing attention inward. There is comfort in its repetition, in the knowledge that this cycle has repeated since long before us and will continue long after. To sit with rain is to be reminded of continuity, of cycles that dwarf individual lifetimes yet touch them tenderly. It is chemistry in service of calm, molecules writing a score that nourishes the land and quiets the mind. In cities, rain reflects human presence, acidic, soot-laden, sometimes harsh. In forests, it carries the fragrance of soil and leaves, softer, more nurturing. These contrasts remind us that rain is never neutral. It speaks of its journey, of the particles and gases it met along the way. Every raindrop has a biography written in chemistry, and every shower is a chorus of such stories falling together. To step outside during rainfall is to be touched by the atmosphere's memory. The poetry of rain lies in this interplay between fact and feeling. Hydrogen bonds, polarity, refractive indices, these are the mechanics of rain. But rhythm, fragrance, calm, and renewal are its human meanings. Rain nourishes crops, cleanses the air, and cools the earth. But it also nourishes us in quieter ways, soothing the mind, steadying the breath, and reminding us of patterns larger than ourselves. In the end, perhaps rain is both teacher and companion. It teaches through its chemistry, how molecules interact, how cycles endure, how even the smallest droplet carries immense complexity. But it accompanies us too, offering solace through its rhythm and beauty. The molecules may fall indifferent to us, yet we cannot help but find meaning in their descent. Rain becomes not just a chemical process, but a partner in our experience of the world. And so the raindrop, humble though it seems, is both fact and poem, both science and song. To study it is to uncover invisible structures. To feel it is to hear the heartbeat of the planet. In each falling drop there is knowledge and comfort, rigor and rhythm. The chemistry of rain explains the how, but the experience of rain gives us the why. As the final drops of this exploration settle, it is worth pausing to ask a gentle question. If every raindrop is both molecule and music, both science and solace, then what is it whispering as it falls from the sky into our waiting hands? Rain is never only weather. It is cleanser, rinsing dust from air and leaves. It is nourisher, soaking soil and carrying dissolved nutrients to roots and rivers. And it is storyteller, a drop-shaped archive of the air it passed through, the particles it carried, the chemistry it performed on its way down. Every shower is a quiet exchange between sky and earth, a reminder that the simplest things often carry the deepest connections. Whether or not we pause to notice, Rain is always at work, balancing soils, fertilizing forests, refreshing oceans, and even shaping the air we breathe.